Yeah. Okay. Hey, everybody. This is session 6, I believe, 6 of 7, studying harmonic experience this summer of 2021. And we're going to be talking about equal temperament today, talk more about the commas that we talked about last week, and talk about augmented 6 chords and fun things like that. Okay, so here's the first thing that was a big aha for me this weekend. I started to understand some of that. The thing is, there are 4 commas, right? The first one that first comes to us historically is the Pythagorean comma. This is telling us, if you look at the page, it says the commas compared. Let's keep referencing back there. On page 53, 4 commas compared. So the Pythagorean comma tells us that 3 does not equal 2. Right. 3, which represents the perfect fifth, does not equal 2, which represents the octave. They'll never meet. So when you think of what we call the circle of fifths, there really is no circle of fifths, because a circle of fifths would have to say that as I went all the way around the circle, I came back to the exact same note, which was C. But we don't get there. We don't get there. What do we get? All right, so let's start from the lowest C possible. Let's go an octave below that. So A, B, B. So we hit that C, and then we come up an octave and we hit this G, which is the perfect fifth, right? And then still A, B, B. And then where do we go after that G? We go to a D. Let's put it in the right octave now. So here's the D. And each of these are a tripling of each other. They're the third partial of the last one, right? So this is on our lattice when we multiply by 3 every time we go over another perfect fifth. 3 to 1, 3 to 1, 3 to 1, 3 to 1, all the way across. So C to G to D to A to E. Say it with me. Where do we go after E? B. Where do we go next? F sharp. C sharp. G sharp. D sharp. Now I'm gonna have to take it down an octave. A, B, A. A sharp. I'm running out of space. E sharp. And next. Oh, this is terrible. Okay. Yeah. Okay. So let's try and move some of this up. That's funny. G sharp. D sharp. A sharp. E sharp. And then way above that, it's already when I start A, B, A. Okay, and then 1, 2, there's E. Here's G, and here's B sharp. I'm sorry, it's really totally messy. Okay. So the thing is, we stack 12 perfect fifths and we get to a B sharp, right? The note is B sharp. The note is not C. If we stack octaves instead, let's start from this low C and then go up another octave to this C first, and then here, and then here. And then if we want to say that we're cycling back around to a C and then go up another octave from there. The point is, this C and this B sharp mathematically are not the same ratio. If we're really listening to, and music doesn't work this way, we don't go in perfect fifths in a real piece of music. We don't hear a music that is balancing out 12 perfect fifths at the same time, right? That's not how music works. We have Pythagorean stuff, but then we also have pentamerous mixed in. So we get lots of different kinds of moves.
So the Pythagorean comma isn't really functional musically, but we should understand the math because it's the first thing that showed up. So when we look at this times 3, times 3, times 3, times 3, times 3, all the way up there, it'll never equal the same number as times 2, times 2, times 2, times 2, times 2, because 2 does not equal 3. 3 does not equal 2. Which note is sharper? The B sharp or the C? The B sharp turns out to be more sharp than the C. This note is higher in pitch than this note by about 24 cents. B sharp is sharper than C by 24 cents. Now let's break it down. If a half step or a minor second equals 100 cents, right? How much is a quarter step? 50 cents. And how much is an eighth of a step? Womp, womp, womp. Shaving a haircut. 25 cents, right? So the Pythagorean comma is just about an eighth of a tone difference. That's how different the two pitches are from each other, right? So what do? There is no such thing as the circle of fifths, which I teach every year to my students and have been for years. But the circle of fifths does not actually exist. So what do? Well, let's see, 24 cents, 12 perfect fifths. If we shave off, because it's too wide, if we shave off 2 cents for every one of those perfect fifths, we can lose the 24 cents. So we go to our piano tuning, and Art brought his piano tuning tools today, which is cool. So we tune each perfect fifth down. We shave off 2 cents off of every perfect fifth. Then our 12 stack will equal not a B sharp, but a C. And we will have a circle of fifths, right? Our circle of fifths will work because when we go all the way around, each fifth is less by 2 cents. And when we get back to there, we've made up that 24 cents. We've taken it off. So equal tempered perfect fifths then are 2 cents flat. Is 2 cents a lot? No, because a perfect fifth is 702 cents. An equal tempered perfect fifth is 700 cents. And we have a circle of fifths, and it works. Okay. So that was my big aha moment. Oh, it's a 24-cent comma. If we take off 2 cents for each of the 12 perfect fifths around the circle of fifths, we get back to C, and it works, and it becomes cyclic. And that's why we can do that. Okay, that's the Pythagorean dimension. There goes the air conditioning. Questions about this? Any questions? Kind of sinking in? Yeah.
So like the circle,
Okay. Now, we can't really use that. It's not very usable. The one that is usable is the didymic comma, the second one, and also the great diaesis, which is probably the most audible, because the didymic comma is very practical. It shows up in some really pretty standard harmony, diatonic harmony. We can see it appearing. But the great diaesis, so let's see, the didymic comma then is about 22 cents difference from one D to the other D, from the 9/8 D to the 10/9 D, or from the 5/3 A to the 27/16 A. It's a difference of about 22 cents, still about an eighth of a tone. It's audible, you can hear it, and you can sense it on the equal tempered keyboard, even though the pitch doesn't change on the equal tempered keyboard, you can still feel it, right? So D to D, A to A, these two that show up in the key of C, or the second scale degree and the sixth scale degree, you have to deal with the didymic comma in any standard diatonic music. The next one is the Great Diasis, and the Great Diasis is about a 41 to 42 cent comma. Well, that's a lot. So you can really hear that one, but it's a little harder to evoke it and to make it come out. We're going to talk about that in a minute. And then the diaschisma is the one that kind of gives us the energy of dominant seventh chords and augmented sixth chords. So we'll get to that today too. Okay. All right. Now that we know kind of what's happening in an equal tempered world with perfect fifths that are flat by 2 cents, as the book says, welcome to the West. This is how our perfect fifths work. You have to really train yourself to be able to hear a 2 cent difference out of 702 cents. And I don't hear a difference. So when you're playing perfect fifths on the piano, they're as close to just intonation as you can get. Okay, so which is why they're good for drones, to sing notes over those, to hear the different kinds of resonance. Okay, let's see. I've got a short video over here. You guys might have to come to me if you're not on a device. And let me share screen. I saw two interesting things, one about equal temperament, one about A440 and where that all came from. So let's take a peek. I put them on Montoya's Great Music Theory. Where is my Montoya's Great Music Theory practice? .wavely.com. There we go. Okay. All right, so let's see these as we talk a little bit about equal temperament. So here I have put the video that Art gave to us, which is Rhythm Becoming Pitch, a wonderful video to watch there. It's now available to you. Thank you, Art. Here's how A became 440. Check this short video out. You've heard of him? We've been talking all prime numbers. Yeah. Third partial. Isn't that fascinating?
Yeah.
Yeah.
Well,
Okay.
that reminds me of that they tune church bells. And so they bells make different tones because of the thing. And the standard way to do it is to tune the root, and instead of the fifth partial, you tune a minor thing.
Oh,
And then they also the second partial is no, no, third partial is really strong.
hmm
And sometimes when your bells go away, you hear the third partial stronger than the first
oh,
one. But what really fascinated me was that instead of the fifth partial, they tuned the third.
yeah. Yeah, that's weird.
And you can actually make a bell that tuned to the fifth partial, but it has a different shape. It looks kind of bad.
Oh, interesting. Uh-huh. Oh, yeah.
Yeah,
Yeah.
yeah, yeah, it is.
Yeah. I've got this article over here. If you guys come check this out. This is from the Encyclopedia Britannica about equal temperament. Let's see what they're saying. Music, a tuning system in which the octave is divided into 12 semitones of equal size. Again, it doesn't have to be 12. It could be 14. It could be 19. It could be 30, right? Doesn't matter because the pitch is a continuum of frequencies, and you could have as many notes as you want in there. It enables keyboard instruments to play. I should be sharing this. Hold on, sorry about that. There we go. Okay. All right, there it is. So this is from the Encyclopedia Britannica. Minimal flaws in intonation, but there are flaws in intonation compared to just intonation if you're playing an equal temperament. Replaced earlier tuning systems based on acoustically pure intervals, that is, intervals that occur naturally in the overtone series, for a more technical blah, blah, blah. Okay, the search for satisfactory tuning systems parallels the development of the Western tonal system with its reliance on enharmonic equivalence. F sharp and G flat sound the same. We know now that in just intonation, they are not the same. And multiple major minor keys. In 1581, Galilei, father of Galileo, proposed a system of equal intervals in tuning for the lute. Chinese prince and musicologist Zhu Jiayu in 1596, and French philosopher Mersenne in 1636, among others, wrote of such a system. The ideal of equal temperament has its most effective advocates among the German musicians and theorists, beginning with Werckmeister in the early 18th century. Even before the system was widespread, equal temperament was approximated in various degrees as a practical matter in the small adjustments made by organ tuners and harpsichordists. Adopted in France and Germany in the late 18th century and in England in the 19th. Et cetera, et cetera. So you can read there more about equal temperament if you like. I don't know if that video had anything. No, that didn't have it. So that's a nice little thing. Oh, wait a minute. Well, let's just look at this last paragraph. In equal temperament, each semitone is measured at honored cents, measuring by frequency or vibrational cycles per second. Remember, it's not just a string going back and forth. It's three-dimensional. So you have the 1-to-1, you have the 2-to-1, the 3-to-1, the 4-to-1, all those different partials being created by different ratios of the string that is being vibrated. The 12th semitone, which completes the octave, therefore, okay, standard A measures 440 hertz. That's why we know now why the octave below 220 hertz and the octave above 880, because every time you double it, you get an octave. Because equal tempered tuning is calculated by subdividing the octave, it is called a divisional system. Early European tuning systems such as mean tone temperament and just intonation were cyclic systems, in which given intervals were calculated by adding together other pure intervals. That's the compounding, I think, of the that we see on the lattice. Such systems accumulate international differences as they move to more distantly related, intonational differences as they move to more distantly related keys, those with increasing numbers of sharps and flats in the key signature. With the result, keyboard instruments and other fixed intonation will sound unpleasantly out of tune in those keys. In other words, music that would sound perfectly in tune in C major with no sharps or flats would sound wrong if transposed to B major 5 sharps, because all the intervals would actually be in different in 2 keys. In equal temperament, the perfect fifth, such as C to G, is narrower by 2 cents, Pythagorean, nearly imperceptible, as we've said. These small intonational defects, it says, are equally distributed among the 12 tones of the chromatic scale, and only one, the octave, remains an acoustically pure instrument. There you have it. That's a good kind of review and another view of what we've been talking about. Okay, there's equal temperament. Questions, comments? All right. Tell me, how do I get out of here? There we go, okay. Tell me what I'm playing. What chord progression am I playing? Right? 1, 4, 1, 5, 5, 7, 1. Okay. That we know. We've learned that since college music theory and even before. Our ear is familiar with it. Our ear gets it. It is pentamerous or Pythagorean. It's Pythagorean. It's moving by perfect fifths, right? Up a fifth or down a fifth to the 4, back to C, and then up a fifth, and then back to C. And it keeps rocking back and forth. We know how to do this. Some say where rock and roll gets its name because we're rocking and rolling between the dominant and the subdominant, right? And we're doing this. And we keep ending up back at C. So there's a perfect going up, overtonal, and a perfect coming down reciprocal. We hear it upside down and come back to C. But what we don't know so much is the pentamerous direction of moving between a major third up and a major third down. Does this sound familiar to you? Doesn't sound very familiar, right? This is the rocking and the rolling in the pentamerous dimension. We go up a major third, which is the fifth partial, then we come back and then we go down. Right? So here's the point. If I keep going higher than this E, what's the next major third up? G sharp. Okay, so we've got an A flat down here. We've got an E up here, which I just played from C major to an E major chord, which includes a G sharp, and then back to C, and then down to A flat. Is A flat and G sharp the same thing? No, we know that it's not. We can figure out the math if we want to. So what do we do? Times 5 times 5. That's 25. And the bottom will be 16. 25 to 16. Make sure I did that right. So we got a 25 to 16 G sharp, which is up around here, which gives us, if I extended this lattice or had more board, you would see that there's this major triad here, right? And then that could be connected to the A, because there's ACE, which is A minor. The G sharp of A minor is different than the A flat of C minor. This one's 8 to 5, this one's 25 to 16. A flat and C sharp are not the same thing, right? So let's review here. we are looking at the great diasis. Saying that properly. What page was I on? I was looking for it before we started. Hold on. And there's a great little exercise in here I want you to do. Okay. Okay, so if you go to page 290 in the book, and actually before that, we're talking about the great diasis. The great diasis tells you, let's go back to our 4 commas compared on page 253, that 5 is not 2. If I stack octaves on top of each other, like we did with the Pythagorean comma, if I stack the octaves on top of each other, it's not going to be the same as if I stack perfect fifths. So let's do this for comparison. Let's start with an A flat down here. And then we go up to major thirds. Okay, no, let me see. Oh, wait a minute. I'm sorry. Okay, so look at top of page 252. This is the easiest way to see it. Let me start over here. In fact, we only need one step to show it. Okay, if I start on C and I stack perfect fifths, E major, or sorry, E natural, G sharp, B sharp. Now this is getting to the B sharp by stacking thirds. It's not stacking fifths. So this is the different one. This is the great diasis. This is the one is about a 41-cent comma. So you can really hear this one, right? Okay, or at least you can sense it more readily than you can sense the other ones. Because it's about 41 cents, which is about a quarter tone. So that and this, octave representing 2, thirds representing fifth partials, 5 does not equal 2. This is what we're talking about. So it's a different kind of B sharp. In this case, the C is actually higher in pitch than the B sharp. The C this time is higher in pitch. And these are cyclic too, because if I can have a circle of fifths. Can I have a circle of thirds? Well, let's see, C to E to G sharp. This is not scale, to B sharp. Well, that would be the same thing, but it's not. So I got to do some things to be able to get it to be cyclic and to come around to the same tuning, because 5 does not equal 2, right? Fifth partials are never going to equal the same as second partials. So this B sharp, the difference between this and this is about 41 or 42 cents. Each third is 14 cents off. So it comes out to maybe about 14 cents. So it ends up coming out to about 42 cents, 41, 42 cents. Okay, now go to page 290. And let's look at some of these. Okay, bottom of 290, you're going to see example 30.13. And listen to this. So let me ask you to focus on the G sharp of the A minor, which is the bass, and then the A flat of the C minor, which is in the soprano part. feel different. The A flat doesn't feel like the G sharp. G sharp is related to the subdominant side, the A minor, which is on the subdominant side of the lattice. And then the A flat is related to the dominant side on the reciprocal end. On the reciprocal side. Let's see again. Well, here's the G sharp, which is related to A minor, which is subdominant from C, right? But if we go to G, to the dominant side, and now we see that C, G, D, A flat, E flat, B flat, there's the C minor scale, right? If you include the F. So this side is C minor. That A flat is 8 to 5. That G sharp is 25 to 16. They're the same on the piano, but we sense a difference. When we sing them in just intonation, we'll hear the difference even more because it's a 41% comma. I'm going to pause this just for a moment. And we're going to learn these parts. Okay, so let's look on page 291, example 30.16. We just had a wonderful time singing through these examples to get them just right before we record them. So I'm going to start at 30.16. I want you to hear that the A flat is actually higher in pitch than the G sharp, which is lower in pitch. So here's the C. Now we'll all sing the A flat. There are 3 blind mice. One more time. Yeah, that G sharp falls.
Right.
And if you can't feel that yet, go back and keep playing it over and over again and singing against those 2 notes on the piano. And you can feel it. That's the great diasis, right? That's the most maybe sensible of all the commas. You can really catch that one. Now we'll put it into example 30.13. You're going to hear a G sharp. So this refutes what we were talking about, saying that the G sharp was closer to the A minor, so you sing it higher. It's actually lower. It feels, yeah, let's see. To me too. Maybe we're missing some. Okay, we're gonna sing this through so you can hear it. Or just type 2. Okay, Tom, the top part, I'll take the middle, Art will take the bass. Okay, and so we're listening, if you're looking on page 290, example 13, you're listening for the G sharp of A minor chord and the A flat of the C minor, or at least the C minor key, right? It's related to C minor. Okay, so G sharp and A flat, great diasis. 2, 3, and do, do, do. Oh, yeah. So that's a wonderful exercise if you can get 2 other singers together to sing through these parts. You feel it different than when you just play it in equal temperament. You can sense it in equal temperament, but you can sense it even more in just intonation. I hope you could hear that pretty clearly. Okay. That's the great diasis. Isn't that awesome? Now there's a wonderful exercise here, and I'm going to actually suggest that you mess with this a little bit. Look at the bottom of 290, the last paragraph says, try to improvise freely using the key scheme C major to A minor, back to C major, and then to C minor, and repeat that many times. Be sure the tone of G sharp in A minor and the tone of A flat in C minor. Be sure to use them. Try to bring each realm into being with an economy of means as suggested in example 30.13. Okay, so go play in C for a while. And just kind of keep going back and forth. All right, you guys go try it. Find a piano. One can use the room there. One can use this piano.
No, you add a third and a third, and you get 96, 7 fifths. So you gotta subtract one.
Oh, okay, yeah. So we're talking, I sent everybody off to the pianos to go and experiment with this, and they came back with some wonderful observations. I'm sorry you didn't get to hear it, but that's what you get being here with us. This would be a great thing for you to go and do, and that is play around in the key of C. I don't know if I played it before. And then switch to modulate to A minor by means of the G sharp. And then back to C. Always use the dominant 7 to get you there. What if you switch to minor? And when you hit the A flat, it's not a G sharp anymore, it's an A flat. Does it feel different? Back to well, it's the same note I was playing before as an A flat. Now it's a G sharp. And it sounds and feels different. Sorry. So you've got these more clearly in just intonation singing. So grab a couple of friends and mess with that. And then you can also sense it on the equal tempo keyboard, but maybe not as clearly, but you can. So mess with that. I'm going to challenge you guys to do something, and you can make it as simple as you want, okay? But I want you to write a piece, maybe 4 bars long, maybe, yeah, as long as you want it to be. But I want you to use this as a model. I want you to go from C to A minor. And again, these could happen within the space of a bar, just like you see on this example. It's only 2 bars long. And it can be a melody only if you want it to be a melody only. Or it can be a block chord. Here's a C chord, play a few tunes. Here's an A minor chord, make sure that G sharp shows up. Go back to C, then go to C minor, and then go back to C. So follow exactly right there on 290. And then either we'll sing it next week or you can play it for us at the piano, right? So get some practical experience with that comma, with the Great Diaesis, and let's see what you come up with. Again, as simple as you want it to be, or as complicated as you want it to be, however much time you have over the next week, okay? I'm gonna suggest one more thing. I know we're out of time, and we're not gonna get to augmented synchro today, but we will next week, promise. And that is the didymic comma. I hate to give you another thing to think about because we went over a whole lot here today, and it was great watching all of our eyes get all excited when we were hearing these differences. The didymmic comma is much more practical because you don't need to be modulating to hear it. So if I can take you all real quick to, let's go to page 270 in your book. Let's go to page 270, and here's the situation. The didymmic comma. Comparing our commas again, remember that third partials are not fifth partials. 3 does not equal 5. Fifths are distinctly different than thirds, right? So the didymmic comma shows up in the key of C right away. Let's look at our lattice again. From C, you go up 2/5, you get a 9/8 D. 9 vibrations for 8 vibrations. But if you come down 2/5 and go up a third, you get the 10/9 D. That's a different D. But look how close it is to subdominant harmony, FAC, right? Or DFA, which is the D minor chord. So the D minor chord can be connected to the subdominant very easily. They're substitutions of each other, 2 and 4, right? But look at this D minor. D, A, there would be an F down here. So this E minor, this D minor, is connected to the dominant. In fact, it has 2 tones in common with the 5 chord. So this D is connected here as a 9/8 D, which is higher in pitch, and this D, which is lower in pitch. You've got not only 2 D tones, but you've got 2 D minor tones, or D minor triads, which is telling you that as you're playing it, and here's what you've been waiting for, Tom, and you can look at this and explore this a little bit. When you're playing a D minor chord, sometimes you can associate it with first one side and then the other side. And when you do that, people have to change their tuning in order to stay centered in C. Look at this example on page 270, the didymmic comma of the 2 triad. Starts on a C chord, goes to an F chord, and then to a D minor chord. Well, I'm on the subdominant side of the lattice, right? I'm on the reciprocal side. I went to C, to F, to D minor. That D minor is obviously tuning to the subdominant side. And then I go to A minor and back to C. So I'm following not only the chords below, but I'm looking up at the diagram. And then what do? I go to a G chord and now a D minor chord. That D minor will feel and sound different than the other D minor that we just played. Because now it's related to the dominant side. Listen to that 2 or 3 times. So you've got these things going on, right? You've got these 2 different D minors happening, and that creates the didymmic comma, and you have to kind of deal with that. Now, the other part is that sometimes you're holding that D minor chord. Sometimes you're holding the D minor chord, and you go out one direction, and you come back in the different direction. So that's when you got to change your tuning while you're holding the chord. It's one thing to hear it when it appears in 2 different contexts, but what if the contexts are back to back? What if you hear C to F to D minor to G to C? Which D minor was it? Is it the D minor with the F, or is it the D minor with the G? And if you're singing that a cappella, then here's the issue. People are going to have to change their tuning to stay consistent while they're holding the chords, the notes of that D minor chord. So this is something else to think about, and I would encourage you, if you want to know more about this, jump into chapter 29. Now, I've been spending a lot of time this summer in the chapters starting from 27 on. And if I can give you a brief summary, this starts part 3 of the book. Chapter 27 talks about all the commas, and it kind of defines them in detail. Then the next 2 chapters are all about the didymic comma. The next 2 chapters are all about the great diaesis. And the last one is about the diaschisma. The diaschisma gets us into augmented 6 chords. And I promise, Tom, we will talk about those augmented 6 chords in our last session. Tom's been waiting for that. But it's a good chance to read ahead if you want to read into that diaschisma chapter. And if I can figure out why it's actually called diaschisma, I'll tell you that. So I would play with that. The chapter 28 or no 29 talks about didymic parasitones and what you do with those, like 2 D minor chords or 2 A minor chords, also 2 6 scale degree chords. But we're going to write compositions using the chord progression on page 290, or the key progression, right? You don't have to think so much in chords. Just make sure your G sharp appears when you're in the A minor context and your A flat appears when you're in the C minor context. And then we'll see what we come up with next week. All right, everybody, have a great week. See you next week, our last session.